So we're going to continue with our introduction to multivariable calculus. We're going to get to the really good stuff here. Green's theorem, Stokes theorem, divergence theorem. So this is part two of the video I just released before that. If you haven't watched that, the intro to multivariable calculus, the link will be in the description. If you can, on the other hand, understand what's happening on the screen right now, then I don't think that video would be necessary. Firstly, hi, my name is Praneeth. I'm really interested in maths and science, as you can see, and I like to explain maths concepts as a way to help me learn maths and science concepts. So, if you're interested in that, follow along. Ask any questions in the comments below, and I'll do my best to answer. But without further ado, let's summarize what we learned in the last video. So we defined what divergence and curl was, these differential operators, and on the other hand, we defined a lot of integral operators. We had the arc length, we had the line integral, we had flux integral, we had a flow integral. Specifically with the last two, we found out how divergence and the flux integral are related in 2 dimensions at least. That's the first part of the screen here. And then on the other side, we have the the way that curl and the flow integral are related. So the 2D curl is formally defined as such. So we've now found a relationship between this differential operator and this integral operator. And this idea, this concept, is going to take us really far. But before we do that, we need to talk about something called a double integral. So the double integral is trying to find the volume under a function. So, a single integral defines the area under a function in univariate calculus. The univariate just means one variable, normal calculus, right? But a double integral defines the volume under a scalar function. So something like if you have a function, this is like the surface plane of a function. This is defined by the area, the volume under this is defined by the double integral. To see how, if we take the sort of the area in this sort of direction here, whoops, but yeah, here, right, and we can just look at this is the z, right? We know that this is f the y, the integral, the area of this little slice here. And if we take all of these slices, and if you can just imagine them like sort of stacked, like almost like just this way, like they're stacked, like ding, 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 like they're stacked like that, all these little slices along the x, then if we sum all of these slices in the x, we find the volume. And that's the idea. That's how simple it is, right? So, using this sort of new computational technique, I just want to show you how to do it, how to compute it first. But using this computational technique, we can start to find volumes under functions that are defined like scalar valued functions. But first, let's go to an example. So we will look at a function in multivariable calculus here. We're going to define a function such that it takes in both x and y as we've looked at before, and that equals, move this out of the way, f of x and y is equal to um, x plus sine y plus 1. So it uses all of the variables here. Now, we want to integrate that, the bounds of our integration. So let's look at an example, right? So the example I've picked here is a function a function of x and y, such that x plus sine y plus 1 is equal to f of x and y. And we've got two boundary conditions here, so 0, x2 minus pi, y, pi. Now we can choose whichever way we want to do it first. We can integrate first with x and first with y. It doesn't really matter. I'm going to start with x, so we're going to just write our double integral formula. Remember that this is trying to find the volume. So I'll do a little sketch at the end to show what this actually means, right? So we can start off with this, and we'll write in our bound. So the first bound is dx, so that's 0, 2. Second bound is minus pi, pi. So we'll just look at this bit here. So we've just got the integral of 0 to f of x y dx. We'll sub in our sorry, that should be 2 and 0, and that's 0, 2, of x plus sine y plus 1 dx. Now, sine y is just a constant with respect to x, so when we integrate this out, we get half x squared plus x sine y plus x 0, 2. And, 0 it just means all of these 0, so we just have to look at 2. So half times 2 squared is 4, so half times 4 is 2, plus 2 sine y plus 2, which just equals 4 plus 2 sine y. Now we can substitute that back into our integral up here, so we have minus pi transforms to 4 plus 2 sine y dy. So we just integrate as normal, 4y plus, and this should be minus 2 cos y of pi minus pi. So you have 4 minus pi minus 2 cos of minus pi minus 4 pi minus, what's it called, sorry, minus 2 cos of, I flipped the bounds around, sorry, my bad, pi minus pi, so this should be um, pi, should also be pi, and this should be 4 minus pi. You have 2, I'm going to write that in a new line here, minus 2 cos minus pi. So that's 4 pi. 2 cos pi, that's just, that's minus 1, but that's going to cancel, so that's going to cancel this, because we'll see in a second, but cos of pi is minus 1, so that's plus 2. That goes to 2. Minus, minus 4 pi, so that's just plus 4 pi. Minus, and then, 2 cos of minus pi is the same, so it's just, this is going to be 2 as well, so minus 2. That cancels, so we're just left with 8 pi, and that's our final answer. So the integral, so basically the volume under this function between minus pi and 0 and 2 for x and y is 8 pi. Right, so now that we know how to use, and let's just check the answers, right? Oh, the answer is 8 pi, so, we got the right answer there. But now that we know how to compute these, let's move on. Let's try to extend this idea a little bit. So let's say we define this parametric surface, and the function that takes it in is something v, and it takes in t squared, and it outputs t squared sts, where t and s are two parameters. We can take more than one parameter. So if I was to sort of sketch that, that you have x, y, and z, um, you can sort of sketch this as like this sort of, it's more it's not as curved as this, but it's some sort of surface here from up above the plane here. And in fact, so now that we've looked at how to compute double integrals, we can now sort of extend the idea, sort of bend it a little bit, and you'll see what I mean here. But first, let's just check if we got the right answer. We did. That's really good. But let's check. Let's expand this idea. So let's say I have this sort of function, and I'm going to just sort of sketch a really rough diagram here, and we have this sort of curved surface here. That's Z, and it's always going to be, this is a parameterized, I'm just saying v of t of s gives us this vector output, right? When we want to look at the surface area of this defines like a plane, and we want to define this sort of surface area minus 1 t 0 s 3. So we have the surface, we have this sort of boundary conditions, first, what we can do, and the problem here is that, like, trying to find the surface area of something curved is going to be a little bit difficult. But we know how to find the surface area of something that is flat. So that's going to be our trick here. So we're going to look at the parameter space where the axis is not in x and y's, where x is a function of t and s and y is a function of t and s. It's just going to be t and s itself, like t and s itself, right? In such a place, we can see what the area would look like. We've got the surface area well bounded. We've got -1 to 1. You've got 0 to 3. This is how it should look like. This is a rectangle. This area is given by summing ds and dt, right? So this rectangle is then transferred onto the surface. Like this is like if you think about this rectangle here, it goes into this sort of curved surface, but it's a little bit distorted because it's non-flat. So there's a scale factor here. So if we can calculate this flat area and then a way to calculate this sort of the scale factor, then we've found what we want, this surface area of a curved surface. More generally, the rectangle is transferred to a parallelogram on the surface. It doesn't need to be, the parallel lines don't need to, they kind of, both lines have to be parallel, but they can start being like squished, right? So the condition that opposite lines are parallel are held, but not the fact that they must sort of be oriented the same way. So the vector describing the bottom, right, the bottom of this sort of surface can be thought of dv dt times dt, right? And the reason why we can think of it like that is that, well, if we just look at it very quickly, well, dv dt times dt is kind of looking like these DTs effectively cancel. Like we're looking at the difference in t and then timesing it by a difference in t. So we're kind of looking at the variation of v, a partial variation of v, right? At the bottom, and the reason why it's the bottom is because of t, right? So we're looking at how much v changes with respect to t there, and similarly, we're looking at how much v changes in that. So like we're trying to define these small kind of variables, right? The reason why we want to don't cancel them is because they're this partial derivative d and this d aren't actually like cancelable. They're not the way we if this was a dt then we can easily cancel it, but this is a like curly d, so it's not cancelable. But the effective idea is the same here. So find the area of this parallelogram, we take the cross product. So we have the bottom and we have a side, so we cross products, and because these two are scalar quantities, we can take them out of the cross product and it just becomes ds dt. So we have this parallelogram, and this then allows us to integrate once with ds, so we get so this kind of line, right? And then dt to extend, like all these slices of s can be put in like that. So first we integrate along this way, then we integrate along that way, or upwards probably. Actually, yeah, probably we integrate down like positive s, and then we integrate right. So that's what gives us this double integral, and that gives us the area of a surface. So this surface area integral is just sort of extending the idea of an arc length integral. And just like how line integrals are related to arc integrals, surface integrals are related to surface area integrals. So this is a surface area integral, right? But we're going to look at surface integrals. So surface integrals are calculating the volume under the surface. So on this surface, right, we want to calculate the volume just around this one, which is, even more complicated. But because we now have a way of finding this area, it's the same thing of we just plug in the function we were looking at inside the integral, and that's exactly what we do. That's the main sort of, these are just new tools that will come up now, but are actually more foundational if you want to do further research. So I just thought I'd explain them before we carried on. We'll go back to derivatives, right? So we've got the first derivative, but what's the second derivative, right? There is sort of kind of like two sort of ways we can think about the derivative, the second derivative at least. And the most obvious candidate would be the Hessian, right? The Hessian is a matrix which contains all positive second partial derivatives of a function, right? And if we set this Hessian matrix, if we find the determinant of the Hessian matrix and look at its properties, we can start looking at the test. So if the determinant of the Hessian is less than 0, then the point is a saddle point, so it's here. A saddle point means it's increasing in one way and decreasing the other, if you remember this from the previous video. And if the determinant of the Hessian is greater than 0, and the second partial derivative of x with respect to x is less than 0, then the point is a local maximum, else the point is a local minimum. So this is kind of replacing the way we would use the second derivative in single variable calculus to classify different types of minimum and maximum stationary points. I want to very quickly talk about the Laplacian as well. The Laplacian is just is defined as this nabla squared. What it just means is it is the nabla dot nabla f, which we know this is the gradient and we know the divergence. So this is showing how quickly that the gradient field is changing. So we have to understand how we've actually broken the two properties we were using the second derivative for. One was for classifying um, sort of points of inflections, so classifying points of inflections. And the other way we're using it is to say rate of change of f. So the Laplacian takes this property. This is the way that this is the most natural candidate to look at how the gradient itself is changing. Whereas the fact that we can use the second derivative to classify points of inflection is done by the Hessian. So you can see in multivariable calculus things that we were doing with one tool that was being kind of, we had like a toolbox, right? If you think of a toolbox, what was once a hammer is now very specific. We can only use like a wood hammer or like a metal hammer. So we're sort of, as we increase the complexity, we cannot use the same tool again and again. Hope that makes it clear. Now let's extend things to the third dimension, right? So flux in 3D is the same idea as flux in 2. We're going to look at how much stuff exits the boundary per given time. The 2D case, it was a line segment, ds, and the 3D, we're going to look at d sigma. I mean, it's not s and sigma. Sigma is the lesser s in Greek, so, ooh, scary, but it just means that we're looking at like a surface here that is d sigma here. The line, so we're going to look at the way we calculate area of a parallelepiped. I mean, if you know this from, even from further maths or somewhere else, it's pretty straightforward. This is like our v term from before. This actual the thing exiting out at that point. And if we take this and we look at the that's given by the vector field at that time t, and in a short space delta t, how far it's going, right? And this is the sigma, like this whole area here. Well, if we dot this with n, we get the height, and the base times height is going to be your volume. So you can see that here, f dot n times d sigma gives you the volume. Now to sum over that, and that is per time. That's the amount of stuff that's leaving per unit time. So now to sum over the entire closed volume, you use a surface integral where you want to integrate over d sigma. And the reason is this sigma is actually a way of enclosing sort of this boundaries here, but we don't know what d sigma actually is. So that's what the next part is. So we have to look at um, d sigma is equivalent to the partial derivative. This should be partial derivative s that we looked at area, the parallelogram here. So that's what this is. It's just another way of writing that. Firstly, we should probably look at how the unit normal vector is also calculated in a parametrized surface. We looked before that dv dt gives a vector tangent to the surface in one direction, and dv ds gives another tangent vector perpendicular to dv dt, but still tangent. Okay, so if you have like a surface that's a bit curved, I'm gonna just curve this a bit. You get, let's say, vt. Okay, by the way, vt just means a dv dt. It's just another notation. And then you have vs. So these are perpendicular, but they're still tangent to the surface here. And to find the unit normal vector, it's actually just enough to cross these two vectors together and then divide them by their magnitude, because it's not guaranteed that these are unit vectors. So if you just take the cross products of these two and then divide them by their magnitudes, it's happy sailing. This should be there should be boundaries there. So the magnitude times the magnitude. So that's a scalar. You get a cross product, you scale it. That's how you get this normal. So quite easily calculated. And this double integral comes because we're doing it over a surface, right? We're looking at t and s. So that's the one's for t and one's for s in no particular order. So this is the second part we have to kind of notice. Well, we've defined flux as how much water left a region, and divergence is how much water left a point. Now, divergence is interesting because it kind of carries on to higher dimensions. It is just the nabla just now has an extra dz, sorry. But now we can define this region. We're now not calling just R, we're calling it region R, and we do the same trick of scaling it. So we looked at the integral from before. This is just the integral on the last slide, and we divide it by the region we're looking at, and we make that region go to 0. So that's the trick. Curl defined how much water curled around the point. Sorry, that limit also, by the way, I think it's not clear in the last video as well. This limit is just the part of latex, really. This limit is it's 1 over that limit. Not actually, but you can take that out. That doesn't matter, but it should, being more mathematical, be the 1 over that limit. Um, Curl define how much water curls around a point, and flow integrals define how water curled around a region. So we give the curl f and we dot it by n because we only want to look at the curl that happens on the surface, right? So if you have this is if you have like a whole surface here, it's very hard to see. I'm sorry about that. And you want to see how much stuff is moving here, you take the normal vector at that point and then you curl, and that just allows you to do only what's happening on the surface and not something that's happening nearby. And again, the integral kind of generalizes. This time the integral generalizes to higher dimensions. So there you go. So we've now extended our functions to 3 dimensions. And now we're finally ready to look at the theorems, the part why you're here, the reason why you're here. So, where is it? We have Green's theorem. First theorem, right? So we've on the last slide, we saw how a global property of a vector field is related to the local property, like the flux integral and divergence. They're linked. We can utilize these relationships to derive some important theorems, right? So the first one is Green's theorem. Let's say we're on a boat and we're on this path here, and we're here. You can we look at the circulations. So you want to see what is the amount of curl that's happening around the boundary of this, right? So that's the idea. Circulation, remember that concept from our flow integrals from earlier. So we're looking at the circulation of this region. And what we can do is we can cut this up into 4 regions, right? And we look at the circulation of each. Now, if we calculate circulation of each and we add them up, can you notice how this is going in one direction and this is going in the other? So these cancel. So all the lines we add effectively cancel. So we can add as many lines as we want. So we define these all to be smaller regions, and we just take smaller and smaller regions and we look at the curl in them. The circulation of them, and I've kind of given it away there. We just kind of look at the curl inside each of the regions, which we can do. It's much easier to do the differential operators rather than the integral operators. So I'm going to just sort of summarize it here. Take a sum, k equals 1 of ck being these boundaries here, C4 and stuff, of k is equal to the total circulation because all the inside stuff cancels, right? All the lines we add cancel because they go in the opposite directions. You take a region R with the boundary C, you want to know the circulation around the region, so you want to solve this integral here. That's the idea. But using the formal definition of the 2D curl, we can rewrite the definition. Can you see how it's normally 1 over RK, right? And I've times it on the other side, and you get this approximation. Not this approximation if this was a limit, but because there's no limit as RK goes to 0, it is an approximation for now. And now you can sum these regions as such. And then if you want to take that RK to be dA, oh my god, you can have that RK to be dA, and then this Riemann sum becomes an integral, then this becomes an equal. And therefore we have defined that the circulation around a boundary is equal to the double integral on the region dA of the 2D curl of f. Look at that. That is a differential operator that is linked now we've in a useful way to an integral operator. This is kind of just falls out of the definitions we're saying. I mean, Green's theorem was revolutionary for the time, but if you just defined your 2D curl as this, it kind of falls out of the algebra. This is called the circulation form. So it's a flow integral. But we can use a flux integral with the same kind of technique, the same sort of thought process, and we get this result, which is very similar. It's just that the now we're looking at how much stuff is coming out, and therefore we use divergence instead of curl. That's known as the circulation form of Green's theorem. This is known as the flux, the normal form of Green's theorem. Both are called Green's theorem, which is confusing because this is just a 2D situation. But now we can generalize just the circulation form of Green's theorem to 3 dimensions, and that's called Stokes theorem. So now, what's the formal definition? Well, that's the formal definition I wrote earlier. We then take this r out, right? And then the limit as r goes to 0 is just d sigma, and then we sum over all of these, and therefore that becomes a Riemann, like this Riemann sum becomes an integral, and we get this S is just this sort of surface boundary there, and therefore this is, look how similar that is, and that's our final result. That's actually Stokes theorem here, so that's why I boxed it. So we get our Stokes theorem just the similar way, looking at the definition of curl in 3 dimensions, and it kind of just falls out from there. And the divergence theorem is very similar. So Stokes theorem looks at surface of console, but what about flux of a volume, right? So we use the same principle. We divide the volume up into infinitely small regions, calculate the divergence of such regions, and multiply by the volume of said piece, and then sum it. So you take a small volume dV, you find the divergence at the point delta, nabla dot f, which is inside dV. Then you sum the product of the two, and thus we do this. So I mean, you have to sum. So you have nabla dot f dv, and because v is actually just here dy, dx, dz, it's in any particular order. There's 3 variables there that you need to look at. So that's where we get this. So that's how we do that, and we know that's equal to the flux of the volume, which we defined earlier. And there we go. We've got the divergence theorem. So can you see from how we've defined and we looked at the links between the differential operators and the integral operators, we can sidestep a lot of rigorous math and actually get to defining the theorems almost as tautologies. Like these theorems fall out if you define your like divergence and curl in a specific way. So that's what makes them really powerful, right? And this is used in electromagnetism most of the time, and this can be extended for many more results, like Gauss's theorem and so forth, fall from this. So I hope you found this video interesting. There was a lot to this, but this is like a conclusion, a little bit shorter than last video, and I hope that you can use this in the research you're doing. Hopefully this gives a good basis of understanding for whatever you proceed to do in the future. If you like the video, please like, comment, and if you have any questions, comment down below and I'll try my best to answer. It was a pleasure having you here. My name is Praneeth, and I would love to see you join me for my journey as it continues. Thank you.